All right, day 2, unit 7. Today is a collection of a number of things. They're all small things. They're all easy things. It's just like 3 or 4 different things. 2 Roman numerals, but they each have 2 sort of subpoints. Man, that sounds lovely. First thing we'll do is convert radians into degrees and degrees to radians. Then we'll talk about arc length and sector area. So still kind of continuing with the geometry theme. Like yesterday, my notes are 1 page front and back, so whatever that converts to you. All right, converting radians to degrees. Both of those are units to measure angles. All right, it's like how wide, how far open a door is, maybe. Oh, is it 30 degrees or is it 110 degrees? I'm speaking in degrees because you're more familiar with degrees. You can look at an angle and get reasonably close in degrees because you know what degrees are. You're just not as familiar with radians. But it's very much like feet to meters. Right? If I ask you to estimate the length of something in feet, most of you would be pretty close. If I ask you to estimate it in meters, most of us are like, I don't know what meters is. It's kind of the same thing. You're familiar with degrees. You're not so familiar yet with radians. Let's start with something that's easy to consider, and that's a full circle or one full rotation. So how many degrees is a full rotation? 360. Do you know how far around a full rotation is in radians? Probably don't. That's okay. Do you remember the equation for the circumference of a circle? Pi r squared is the area of a circle. So 2 pi r. And that's because 2 pi is the equivalent of all the way around. Right, just like 3 feet is a yard, 360 degrees is 2 pi radians. And that's not usually the conversion factor we use because it's a little bit easier if we just divide that by 2 and say that 180 degrees is pi radians. That's the big deal. You got to know that conversion to make things work. All right, so we're going to do some examples both ways. We'll convert degrees into radians, and then we'll convert radians into degrees.
What does the word say next to pi?
Rad, radians. So let's start with 60 degrees, and let's convert that into radians. And I think you've all had chemistry. My favorite part of chemistry, because it was the least chemistry part of chemistry, was the train track stuff, the unit stuff. Does that sound familiar? You draw the train tracks out and make all the units cancel out. Like, you kind of didn't have to even understand what was going on, but like 22.4 liters is 1 mole and cancel them out. And it's kind of the same thing here, although it's a lot shorter. I want the degrees to go away, so I need degrees in the bottom. Right, again, I like this in chemistry because you didn't really have to understand the chemistry. You could just make the units work and get the problem right. I felt like I survived chemistry, high school and college, by making units work, more so than understanding what was going on. So 60 pi over 180 radians, but that would reduce. 60 over 180 would be pi over 3. So that means 60 degrees is the same thing as pi over 3 radians.
You put the rad in the top, is that wrong?
No, that's right. You do want the rad in the top.
Well, yours is in the side. I'm talking about like at the top of the...
Oh, you mean at the top of this? No, that would not be wrong. Most people wouldn't, they'd put it over here, but it would not be wrong. If you want like a picture of that, maybe that's 60 degrees. Kind of just eyeballing it. It's a little bit more than 45. In radians, that's pi over 3. Probably 2 or 3 weeks into next semester, you'll be sort of thinking in radians as much as you think in degrees. And that's crazy to think about now because it's a foreign concept, but we'll get there.
So 120 is 2?
So 120 would be 2 pi over 3. How about negative 140 degrees? Why don't you convert that to radians? So again, not real difficult. Make the degrees cancel. That leaves radians in the top. And then reduce. Don't forget the negative. Kind of a dumb common mistake. People get so caught up in the pi over 180 stuff that they leave the negative off their answer. All right, let's do some the other direction, from radians to degrees. So let's start with 3 pi over 4 radians. And Luke, to your point, it's on this one it probably is better to put radians in the top because then it's easier to know where to put the next thing so that things cancel. So this time I need radians in the bottom to cancel. And I know that pi radians is 180 degrees. So pi's will cancel. The radians will cancel. And then 3/4 of 180. Let's see. 1/4 of 180 is 45. Times 3 is 135. So 135 degrees. And again, your brain is still thinking degrees, so you could probably roughly picture 135. And now we know that that's the same thing as 3 pi over 4. You're not memorizing that, you're just thinking about the process of converting. Okay, one more for you to try. Convert negative pi over 10 radians into degrees. Negative 18 degrees. So if you're comfortable with the train track thing, it's really pretty easy. Some people get stuck on trying to memorize, well, do I multiply by pi over 180 or 180 over pi? And I'm like, I don't think about that. Just figure out what needs to cancel and use the train tracks. Right? A super important idea heading into next semester is coterminal angles. Coterminal. Co meaning same. cooperation, you're on the same team. Cohabitating, you're living in the same house. Coterminal, you have the same. And terminal means ending. Right? The airport terminal is where the flight ends. A darker note, a terminal disease means the ending is near. So coterminal means angles that have the same end. So let's maybe draw a picture of a 90-degree angle. Kind of an easy one. So if we wanted an angle that's coterminal at 90 degrees, maybe you're not familiar with this, but negative means you can go backwards. You know how far backwards you'd have to go to land at the same spot? Negative 270. So 90 and negative 270, they land at the same spot. They're like different ways of getting there, but they have the same ending. They are coterminal. Now, if you really wanted to be fancy on being coterminal, you could go all the way around and then go 90 degrees more. That is 450 is right. How did you come up with 450? What'd you do? Say it, because that's... You added 360. 450. And obviously you could spin around 100 times. So 36,000 plus 90, whatever that is. And that would be coterminal. So there's an infinite number of coterminal angles because you can spin around as many times as you like to land there. Okay, so the key to finding coterminal angles is to add or subtract how many degrees? Well, careful. You want to add 360 to spin all the way around. Add or subtract 360 degrees or 2 pi if we're talking radians. I didn't do an example in radians because our brains don't really think in radians yet. But the 2 pi is the same as 360. So add or subtract 360 or 2 pi as often as you want. To land at the same spot. Let's do one with radians, since that's a little bit trickier. Name 3 coterminal angles with 2 pi over 3. 3 coterminal angles with 2 pi over 3. Well, in radians, it's a little more formulaic because you don't know where 2 pi over 3 is, so it's hard to visualize and then visualize adding 2 pi. It just doesn't work with radians like it does with degrees yet. Hopefully you'll get there. But we know what we can do is start with 2 pi over 3 and add 2 pi. Wherever 2 pi over 3 is, let's add 2 pi, and that'll spin us around one whole time. So we do have to know how to add fractions. What's it take to add fractions? What do you have to have? Common denominator. So I need a 3 in the bottom, which means I need a 3 in the top. So that's 2 pi over 3 plus 6 pi over 3 is 8 pi over 3. So there's one of my coterminal angles. But it asks for 3 of them, so how can I get another one?
Add the same thing.
Add the same thing. Do it again. Someone said subtract. It could also subtract. But while we're adding, and I already know that 2 pi over 3, or excuse me, 2 pi is 6 pi over 3. I can just skip ahead and know that I need the common denominator. So 6 plus 8 would be 14 pi over 3. So that would be coterminal. We wanted 3 of them, so let's do that one more time. 20 pi over 3. So all of those angles land in the same spot. One of them is sort of the easy way to get there. The other has an extra spin, and 2 extra spins, and 3 extra spins. Cool?
Would negative 4 pi over 3 work if you subtract?
Yes. So another one would be 2 pi over 3 minus 6 pi over 3 would be negative 4 pi over 3. And I guess if you really wanted to be creative, you could keep subtracting and get negative 10 pi over 3. And then negative 16 pi over 3, and on and on and on and on. So I asked for 3 of them, and how many of them are there? Infinite, because you can spin around as many times as you like. You can add or subtract 2 pi as many times as you like. Let's find 2 coterminal angles. So just 2 this time. With negative 100 degrees. So we're in degrees now, so our brain shifts from 2 pi as a full trip around to 360 is a full trip around. So if I start with negative 100, what could I do to get a coterminal angle with that? Well, I guess there's an infinite number of options, but 2 basic options. Add 360. Give me 260. And then I could subtract 360. Give me negative 460. And that's 2 answers. If you didn't like subtracting, you could have added 360 again. Would that be 620? So I asked for 2, but there's 3 because almost everybody would give me 260, but some would just keep adding and others would go back and subtract. But it doesn't matter. It didn't really specify. So angles to degrees, radians to degrees, degrees to radians, and then the coterminal thing is just add or subtract 360 or 2 pi. Roman numeral 2. Arc length and sector area. You kind of know these already. You know it for the full length around, for a full circle. So what's the arc length? What's the circumference? That's an arc length. It's just the full arc. What's the formula for the circumference of a circle? 2 pi r. And how about the area of a circle? Pi r squared. Please don't get those backwards. Right? Length has 1 dimension in it. Area has 2 dimensions in it. So maybe that'll help keep them straight. So you kind of know it already. You know one case of it if it's the full circle. But if it's not the full circle, so let's say we have this situation and we want to know that L. Usually we use like a lowercase cursive L for arc length. Well, the full trip around is 2 pi times r. Thank you. The full trip around is 2 pi times r. But if I don't want the full trip around, instead of using 2 pi, 2 pi is the full trip. I don't want the full trip. I just want whatever theta is. So theta times r. as long as theta is in radians. Which I think makes sense. If theta was in degrees, then the circumference would be 360 times r. That doesn't seem quite right. So there's one of our formulas. The length is theta times r. So it's related to the circumference formula, and I present that to hopefully tie it to something, makes it a little easier to remember. Sector area. Let's use the same type opening so it looks roughly the same. This one's a little bit harder to, I think, make the direct comparison, because on the circumference you can just replace 2 pi with theta. But on the area there's not a 2 pi to replace it with, so it's a little bit harder to think about. Pi r squared would be the full way around, or the full circle, the area of the full circle. And you can think of this as like a percentage or a ratio of the full circle. So you want theta out of 2 pi. That would be theta in radians if you did it that way. This one you can do in degrees. You just need your theta out of 360. So either way you do it, you find the full area and then you multiply by sort of whatever portion of the area you want. The angle out of 2 pi or the angle out of 360. So those two formulas you have to know. Hopefully they're tied enough to things that you already know that it's not too bad. Let's do one example and find both things. That way we kind of condense our examples here. Find arc length and sector area if r equals 4 inches, and central angle, that might be a new term. Maybe use that in geometry, I don't know, but it's the angle at the center. I don't know that we need to define it any more than that. Central angle equals 110 degrees. So let's sketch a little picture here. 110, so that's a little more than 90, so something like that maybe. It doesn't have to be perfect because this is just help us visualize it. Arc length and sector area. Okay, arc length. So in my picture that would be this length. Okay, arc length is just, well, the full arc length is 2 pi r, but I don't have 2 pi, I want to use theta. Except I can't use 110. Right? Hopefully if you're paying attention and you use 110 and your arc length then is 440, it's like, wait a minute, if my radius is 4, then you're going to tell me that this is 440? That doesn't seem quite right. So I need to change that 110 into radians. That's what we did earlier. It's almost like the lesson fits together. Okay, what's the conversion factor for degrees to radians? 180 and pi. Which one's going to go in the bottom? 180, because I want the degrees to cancel. So 11 pi over 18. is my angle in radians. So my arc length is theta, which is 11 pi over 18 times 4. Let's see, the 4 and the 18 could reduce. 2 and 9, so 22 pi over 9. What about units? Degrees, radians, inches squared. Oh, let's see here. Well, think about looking at the equation. If I'm asking for how long the arc length is, what do you think? And the radius is given in inches. It seems like my arc length should be in inches. Now, if we look at the equation, it's a little bit more confusing because you're doing radians times inches. And this is sort of the weird thing about radians, is it's a unit, but if you don't need it to be a unit, it can go away. It's like, wait, what? It's a unit, but it's not a unit? Yes. So the dealing with units and radians is kind of tricky because if you want it, you use it. If you don't want it, you can toss it. And you kind of just have to know based on the picture what's going on. All right, the second question was sector area. So that would be the green area there. So area is pi r squared, but that would be the full area. I don't want the full area. I want some portion of the area. So what portion of the area do I want? What fraction am I going to multiply by? Good, 110 out of 360. So again, is it a new formula? Kinda. You know the full area, and you're just getting a portion of the full area. So pi times 16. Let's see, the zeros will cancel for sure. Times 11 over 36. And then we could reduce some more. Let's see, you could reduce by 4. So 44 pi over 9. And again, you can kind of go through the process of finding the units based on the equation, but it'd probably be easier to just know, if we're talking about area, what are the units? And the units of area. Inches squared. There are a few problems on the homework that ask for these like in decimal, and so at that point you would just go to the calculator and say 44 pi divided by 9 is 15.36 inches squared. So it kind of just depends on how the question is phrased. 44 pi over 9 is an exact answer. 15.36 is an approximate answer. But if you were doing like a word problem, or like in real life, if you're painting a circle in your room and you got to figure out how much paint to buy, well, knowing that it's 44 pi over 9, that doesn't really help you. You need to know, like how many feet squared am I trying to paint here? So that's where you would use the calculator. So it kind of just depends on the situation as to which type of answer is preferred. All right, today's assignment is worksheet 2. We'll answer questions from that tomorrow. But I think it's pretty straightforward. And it specifies on that one whether to use the calculator or not. So you'll know, you could kind of tell by the answer choices. But you'll know going into the problem whether you should use the calculator or not.